Okay, we're going to walk through some search algorithms. So my public class algo, I'm making a global variable iteration counter. It's global because I want to access it outside the main method inside the other like linear search methods. Alright, so I'm going to set the seed to 999, make an empty array with the values of the seed plus 1, of course, because of the starts at 0. And then I'm going to fill this empty array with so many indexes with the actual values in the indexes. So we can do this for loop a million times. You can see it counting up down here. Alright, so let's take off this breakpoint and just go. Alright, so result equals linear search algorithm. So we're going to go to the linear search algorithm. This is a recursive algorithm. I'm returning an int and it's static, because we're in the same class, linear search algorithm. We're sending in the search value, the array, and the index. Alright, so we're adding a iteration counter for the first iteration. So if the index is less than or equal to the array.length, we're just stepping through the index. Well, return -1. This is the base case. This just means that it wasn't found. Alright, let's get past this. Okay, if the array index equals the search value, return index, we're at 0, so it's not. It needs to make this call 9,999 times to get to the 9,999th value. So, and this is what makes it a recursive algorithm, that in the base case. Okay, let's get out of this. So if the result is not -1, -1 means it wasn't found. I'm going to print the result, and it says linear seed value found in result 9999. Else it wasn't found. And then after this, I'm going to print out the number of iterations from the iteration counter. And that should have been in the while loop. So, yep, iteration counter is 10,000. That's exactly what I want to see. Now we're going to reset the iteration counter back to 0 so we can perform a binary search result. So we're sending in the array, the seed. I'm setting low as 0, and the high is the length -1 again because we start at 0. Okay, we're returning an int. It's private and static because we're in the same class. We send in the array search value, low and high. So binary search is like a dictionary. We're going to go to the middle, compare values to see if it's higher or lower, and depending on that, we're going to go in the middle of that block, compare again, and repeat until it narrows down to our item we're looking for. So the first iteration counter, first number of calls. So if low is less than or equal to high, this is basically just checking that it's somewhat sorted. It should be. So our mid equals low plus high minus low divided by 2. We're just finding the middle of high and low by doing this. Okay, so if the array of mid equals search value, return mid. It's not. So if array of mid is less than search value, so we're just checking if it's going to search the right half. If it's less, then if array mid is less than the search value, it's obviously on the right. And it's on the right, but that's not it. That's why we're down here. So we're going to call this again, and we are just stepping through all this stuff again. It actually only does it 12 times, so let's watch it step through there. Alright, so the mid is at 74.99, 87.49, 97.34. We're getting there. 843.9921. Oh, go away. Okay, enough of this. Yep, it goes 12 times. So if the result is not equal -1, which is not equal not found, binary search seed value is found at result, which should be 9999. Otherwise it wasn't found, and then we are going to print the number of iterations. Let's see if I'm right. That's 14. I was close. I've done this a few times. trying to get this video right. Okay, so now we're going to reset the iteration counter for a jump search algorithm. And basically what this jump search algorithm does is it takes the square root of the length and sets it into blocks, the length of each square root, and it searches each block until it finds the right block, and then it searches the sort. So it's like a shortened version of a linear search algorithm. We're sending in the array and the seed, private static int, same as before. And yeah, we got our values up here. Okay, we're just setting length to the array.length for clarity. Step, I'm finding the square root to find the length of the steps. Alright, and then I'm just starting previous at 0 because we want to start our search at 0. And then we're going to count each iteration. Okay, well, the first iteration. Now our while loop. The math minimum is step minus step in the length. We're just setting bounds here. We're making sure the minimum is less than the seed. So we keep walking to look for our, we're stepping through the blocks now, each square root. So the square root of 10,000 is what, 100? So we're going 100 at a time. Yeah. So we'll just take these off and speed this up. Okay, now we're gonna perform the search within the block. Because we found the block, we've stepped through here till this was true. So we broke out of the block. Okay, now we're doing another while block, and instead of just comparing these to make sure it's less than the seed, we're gonna do each value and make sure it's equal to the seed and return previous. And yeah, count the iterations again for this one. And this one should be a lot shorter. Well, no, it should be around the same actually. But I'm gonna skip these. Okay, if the result does not equal -1, it's the same exact line as I did above. I could have made a method for this, that way I wouldn't have had to retype it 4 times. That's probably what I should have done, but well, oh well. I'll maybe do that next time. Okay, so I'm just printing out the result, the iteration count. Oh, I left this inside this block. I did it outside the else block on the other two, but it doesn't really matter that much. Now we're going to reset the interpolation, the iteration counter for the interpolation search algorithm, and this uses a formula that I was given that's actually really accurate. It finds this one in just one iteration, which seems really odd to me. I spent a really long time trying to figure this out, and I even put the numbers in the into the formula, and I guess it comes out in one iteration. If I'm wrong, I'd like to know, but okay, so I'm sending in the array and the seed, that's all we need, and I'm setting a low and a high, just like we did in the binary search. Okay, so while low is less than or equal to high, yeah, and the seed is greater than or equal to array, and the seed is less than or equal to array.high, that just we're just setting bounds to make sure our seed is in the middle, and then we're going to do our iteration counter. And this moves on to our formula. Here's the formula we're going to use. The position that we are at is low plus seed minus array low times high low divided by array at the high minus array at the low. This formula is a little confusing. I'm just using the one that was given to me as the formula. I don't understand how they came up with it, but I understand how it works, if that makes sense. Okay, so if the position equals seed, we're returning the position. This isn't a recursive algorithm, neither is the jump search, because we're not calling it again. Now we're returning the position at position 9999, which it actually found in one iteration. That blows me away. Okay, if the result does not equal -1, which nope, it doesn't, it equals 9999, printing out the value at index and at iteration counter. Let's go over to the console. Here's what I printed out. Linear seed value at index 9999. iterations, 10,000. Of course, because we started at 0. The binary search was the seed value found at 999. The binary search iterations was only 14. That's pretty good. The jump seed value. Why didn't I print? Oh yeah, let's print out the interpolation. Seed value found at 9999. Number of iterations 1. So I was reading that the interpolation can be even more accurate than the binary search if the graph is evenly sorted, which it really is on this one because it found it in 1 iteration. So again, my name is Eli Clemens, and this is my search algorithms.